Hi everyone, my name is Ray, and today I will present our work, Design and Implementation of Web-based speed test analysis toolkit. This is joint work of people from ETH Zurich, Cater UC San Diego, Hong Kong PolyU, and Pengcheng Lab. So let's get started. As you may know, web-based speed tests are widely used in different fields. They often serve as a popular tool for users to measure their internet connectivity. Going beyond, they are also often the core component of many applications, such as video gaming and streaming. They are also cited by government and commercial reports for advertising and policymaking purposes. So how do they actually work? Well, the idea is actually simple. Often you click on the button in the website, and this platform will choose one or multiple of their servers, which are often closest to you, to establish TCP connections with you, the end host. Then they will start with back data transfer in order to saturate the access link. Upon finishing the data transfer, they will return the test results, which usually include the download throughput, upload throughput, and the latency. Here is the screenshot of a test run by Ookla SpeedTest. It shows the server information, which is in Zurich here, and the test result. It sounds simple, right? With one click, you can know your internet performance already. However, in reality, it's actually not that easy to understand the results and further utilize them for different purposes of studies. There are multiple reasons behind that. First, it's burdensome to configure the test execution automatically. Most of these tests only offer a web interface that selects the default test server for users, though in some cases, users can change the servers manually. They don't really have the information of all available servers. Second, all these platforms use HTTPS encrypted traffic for link saturation, which prevents us from having a transparent view of HTTP transaction details to evaluate the performance extensively. Third, despite the many network dynamics, let's say network congestion, these platforms only report a few simple numbers without knowledge of their methodology and the necessary context and background during the execution of the test. It's just challenging to correctly interpret and utilize the results. So considering all these problems, we have the following research question, which is how to build a framework for web-based speed test platforms which can automate the test execution, provide in-depth analysis of test results, and meanwhile, is also lightweight and accurate. We answer this question positively by presenting WebTestkit. WebTestkit is a lightweight framework which facilitates automatic test execution and cross-layer analysis for speed test platforms. Taking the experiment config, for example, including the target server information as the input, WebTestkit will produce the experiment report, which contains the analysis results of the executed tests. For example, the browser overhead introduced to the reported bandwidth and latency. It has three main stages. Let me introduce them one by one. The first one is test execution. In this stage, it uses a unified interface to take the configuration, automates the test execution, and then captures the test result shown in the website. Other than that, it also collects information extensively from multiple layers, include browser data, packet data, and metadata. After the first stage, it proceeds to the second stage, which is performing analysis of the collected data. The main goal here is to accurately capture HTTP transaction details in the encrypted traffic so that we can have an in-depth view for all measurement traffic, from application layer to packet layer. After the analysis, we proceed to the last stage, which is to apply the customized use cases to the analysis data. Some of the existing ones we support include speed test comparison and overhead evaluation. So far, so good, right? But what is the difficulty of building a tool like WebTestkit? Well, the first challenge is that we want to keep the framework as lightweight as possible. Specifically, we cannot really afford the full-size packet capture due to the packet data transfer characteristic of SpeedTests. To solve this problem, it came to our first insight, which is to only capture the packet headers of encrypted traffic. This makes our data collection lightweight so that there is minimal interference introduced. However, since we don't capture the full packets, it's impossible to use the SSL key to decrypt the traffic, which leads to our second challenge. Failing to decrypt the HTTPS traffic results in no visibility of HTTP messages carried in the packets, and this lack of visibility makes a lot of quantification and interesting analysis impossible. To this end, we developed a packet matching algorithm to capture HTTP transaction details and locate the HTTP messages without decrypting the traffic. We fully implemented WebTestkit with 2,000 lines of JavaScript code and 10,000 lines of Golang code. It supports 5 most popular web-based speed tests, include Google Speed Test, Xfinity, Fast.com, SpeedMe, and cross.layer. There are more interesting experimental results in our paper, but due to the time limitation, here we only present one result regarding the speed test comparison. Here is a histogram of the response sizes of HTTP GET requests. It shows a diverse distribution of the download object sizes across different platforms. For example, SpeedMe uses the largest web object, which is 128 megabytes among all tests, while the largest one for Fast.com is merely 24 megabytes. To conclude, we propose WebTestkit. It automatically executes speed tests with lightweight data collection, and it can interpret encrypted traffic for HTTP transaction details accurately. It also enables in-depth analysis of test results. We have open source WebTestkit in GitHub, and thank you for listening to the presentation. I'm happy to take any questions.